So we have looked at programs as functions, and we have looked at data types or types describing the values that a function can take as input and produce as output. So with this abstract background, let us concretely look at the language Haskell, which we are going to use in this course. So Haskell is basically a programming language for describing functions. In Haskell, a functional definition has two parts. The first part describes the types of the inputs and the outputs. What values does this function manipulate? And the second part, which is of course the important part, is the set of rules for computing the outputs from the inputs. So here is a very simple example of a Haskell function. The first line describes the type. So the notation, so this is the name of the function, sqr. Then this notation with two colons indicates that this is a type definition. As we will see, int is a built-in type in Haskell. So int stands for the integers, which are the whole numbers including negative and positive numbers. And finally, this funny notation, which is a minus followed by a greater than, is indicative of the mathematical arrow. Right? So this is true, you will see in many Haskell syntactic forms in Haskell, that we try to describe in characters something that is a familiar symbol from mathematics. Right? So this says that square, sqr, is a function which takes integers as input and produces integers as output. So this is the type definition. And now we have a rule which tells us what to do with a given input. So it says if I'm given an input x, then the output should be x times x, where this is a built-in operation. Right? So this is what a Haskell program looks like: a type definition and a computation rule. Now this is a very simple function with one computation rule. We will see later that you could have more than one computation rule depending on the value of the input. So before we look at how to write more complicated rules in Haskell, let's look at the basic types that Haskell supports. The most familiar type in any programming language is the set of integers, which in Haskell is called int, int, with a capital I. Note that in Haskell, variable names and types and all, the uppercase, lowercase matters, and all types by convention start with a capital letter. So capital INT stands for the set of integers. This is of course the usual set of numbers: 0 plus 1, minus 1 plus 2, minus 2, and so on. And there are the usual arithmetic operations supported in integers: addition, which is denoted plus, subtraction, multiplication, division. But note that division does not produce integer division. It is the regular division. So if I say 5 divided by 3, then I will get a number which looks like 1.666 blah blah blah. Okay, I will not get 1. Integer division is the function div, and remainder is a function mod. But these are functions, so I should write div 5 3, and this will give me 1, because if I divide 5 by 3, it goes 1 time and not 2 times. And similarly, mod 5 3 will be 2. This says that the remainder of 5 when divided by 3 is 2. So I should be careful not to write 5 div 3. Okay, there is a way to write it like this, but not the way I've written it here. Okay, so you can take functions and treat them as operators and vice versa. We will look at this later. But for the moment, just note that when it's a function, you must write it as a function and provide the arguments after the function. And as we saw before, if a function has multiple arguments, you supply them one after the other with spaces, no brackets, no commas. So the other numbers other than integers are of course the so-called real numbers. Okay, and in computer science, they are often called floating point numbers to indicate that the decimal point is not at a fixed position but floating point. And because of reasons of precision, you can only represent a finite amount of information. The floating point numbers do not actually capture all the real numbers. It's only up to a certain precision. But anyway, that doesn't bother us right now. But we have two different types: int, which are integers; float, which are floating point numbers. Then, as we saw before, a very important type for programs is text. So we have the basic text unit is a character, and a character is written with single quotes. So we write the single quote A, single quote %, single quote 7. So any character which we can type on the keyboard can be represented with a single quote as a character input. And finally, a very useful type for programs to decide how to apply values depending on the inputs is the Boolean type. So the Boolean type has two constant values in Haskell, denoted true true with a capital T, and false, falce, with a capital F. Right? So booleans are denoted true and false. So booleans are not 0 and 1 as they are in some other programming languages. So it's a separate type with two specific constants, true and false. So just as we have arithmetic operators to combine arithmetic values like addition, subtraction, and so on, we know that we have Boolean operations to combine Boolean values. So we have the Boolean AND, which is true provided both its inputs are true. We have the Boolean OR, which is true provided either one or both of its inputs are true. And then we have the function which negates the value. Not of true is false, not of false is true. And notice that we use the word NOT. We don't use a symbol for not. And another very useful thing that all programming languages support is to allow us to compare values and then return a true or a false. Okay? So we can have relational operators to compare, say, integers or floating point numbers. So equality, because the single equal to in Haskell will be used for function definitions, as we saw when we said square root of x is x star x. Right? So single equality is really equality in the sense of a function definition. So equality of values, as in many programming languages, is denoted equal to equal to. And then we have less than equal to, greater than equal to. What is probably slightly unusual is the symbol for not equal to. In some programming languages it is written with an exclamation mark. But Haskell, as we mentioned before, tries to mimic the symbols we actually use in mathematics. So this is supposed to be a representation for the normal symbol equal to with a slash across it, which we use for not equal to when we write mathematics by hand. Okay, so just remember that slash equal to is the symbol for not equal to in Haskell, not exclamation mark. So let's now define a more complicated function than square. Let's, for instance, define a function on Boolean values. So we saw the function OR. So we have A or B is true if A is true, B is true, or both. Right? So this is the so-called inclusive OR. Right? So this is true if either one or both of the values are true. The exclusive OR is a function which requires precisely one of the values to be true. So it takes two inputs of type bool and checks that exactly one of them is true. Okay? So now here is our first surprise, that how do we write a function of the type of a function with two input values? Well, just take it for granted right now that we just write the types of the values in succession followed by the output. Right? So this is the input 1, this is the input 2, and the last one is the output. Okay? Why this is the case will become clear a little later in this week's lectures when we talk about this whole notation of functions not using brackets and so on. But for now, let's just assume that a function of many inputs, we write the functions of each, the type of each input one after another separated by this arrow symbol followed by the output type. So a function which takes two booleans and produces a boolean is bool, arrow bool, arrow bool. And what is the rule for this? Well, if I'm given two input values b1 and b2, then either I want b1 to be true and b2 to be false, but b2 is false provided not b2 is true. So I want b1 and not b2 to be true, or I want not b1 and b2. So I want b1 to be false and b2 to be true. So this is the exclusive OR function. So this is very similar to our earlier function which said square of x is x times x. So here we use an arithmetic expression. Okay, and here we are using a Boolean expression. So in principle, there is no difference between a function which takes numeric values and uses a numeric expression, and a function which takes Boolean inputs and takes a Boolean expression. This form is very similar. It's just that we have to be clear about what values our functions are manipulating. So let's look at another function now which mixes the two. Right? So supposing we want to take three integers and just check that the three integers are in order. So we want to say something like in order of say 3, 7, 8, this should be true. But if on the other hand, if I say in order of 7, 3, 8, this should be false. Right? So we are given three inputs and we want to check that the three inputs are in ascending order. So this is now a function which takes 3 ints and produces an int. Now given our earlier discussion about how we write the type, this is the first input, this is the second input, this is the third input, and this is the output. Right? So it is int, arrow int, arrow int, arrow int. Okay, the first 3 ints correspond to the first 3 inputs in that sequence, and the last one is the output value. So it says take x, y, and z. Let these 3 be the input values. Then check that x is less than or equal to y, and y is less than or equal to z. Right? So we are now taking integer values and producing. Sorry, this is not a. It's producing a Boolean output. So it will take 3 integers as input and produce a Boolean as an output. And what it will do is it will apply this relational operator to the first 2 inputs, a relational operator to the second pair of inputs, and use a Boolean operator to combine them. So it produces a Boolean expression from 3 integers. Okay, so this is a function which mixes types from the input to the output. So it converts integer inputs to Boolean outputs. So now let us illustrate more complicated ways of defining functions using the function that we saw before. So recall that exclusive OR is a function which tries to check that exactly one of its input is true. Now in the case of Boolean values, we only have 2 possibilities for the inputs. They are either true or false. So if I have a function with 2 Boolean inputs, as we know, we can write what is called a truth table. Right? So we can say that we have B1, B2, and we have the output. Right? So we can enumerate these things. We can say this is true, this is false, this is true, this is true, this is false, this is false, this is false, this is true. These are 4 possible values, and then we can specify the output. We say that this is okay, and these 2 are not okay. Right? So this is the truth table for exclusive OR. Now we can actually write a function which checks these patterns. We say that okay, if this is the case, then we say XOR of true and false is true. Similarly, if this is the case, we say XOR of false and true is true. And finally, we say that if it is not one of these 2, then XOR of any B1 and B2 which is not of the form true, false, or false, true must be false. So what we are saying is that when we give an input to this function, we look at the input and see whether it matches the definition. So if I give XOR of false and true, it doesn't match the first definition because the first definition works only if the first input is true and the second input is false. So this doesn't match. So you check the second definition. So you go top to bottom. Right? So this matches this definition. Similarly, if I give true, true, it doesn't match the top definition because this is wrong. Okay? It doesn't match the second definition because this is wrong. So finally, it has to fall through to here, and it says, okay, if it is true, true, then the third definition applies, and the answer is false. So what we need to make a little bit more precise is what it means for a function call to match a definition. And that's quite straightforward. Right? So if the argument in the definition is a constant, so supposing I write XOR true, false equals to true, right? And now if I say XOR true, true, then this doesn't match because this is a constant and this doesn't match, right? So if I have a definition which uses a constant, then the function call matches that definition only if the same constant appears in the function call. On the other hand, as we saw before, if we have B1 or B2, okay, then if the definition is a variable, then any value matches that call, and then you substitute as usual. Okay, so this is what we normally use when we have functions. We write f of x is equal to something, and then we write f of 7. Then 7 is substituted for x, and then everywhere in this, if I write x plus 3, then 7 becomes the value here as well, so I'll get 10. Right? So this is how we normally write functions. We write variables to indicate the arguments, and when we call the function with a concrete value, that value is substituted for that variable uniformly in the definition of the function. Right? So this is the usual case, but what is the unusual case in Haskell is that I can give these constant patterns and say that if my variable is of a fixed type, fixed value, then that pattern will be matched and that definition will be used. So we will see more examples of this as we go along. Right? So here is a definition of the built-in function OR, but we are writing it ourselves. So remember that OR, for the truth table for OR is right, that if either of the function values is true, then the output is true. The only case which is outside this is when both values are false. Right? So what this is here now is that I'm mixing constants and variables. It says if the first argument is definitely true and whatever the second argument may be, the output is true. Okay, so that says that I'm either in this case or I'm in this case. Now if I have the second argument true, then whatever the first argument may be, the answer is true. So now I am in this case or in this case. And finally, if neither of these things holds, then the first argument is not true and the second argument is not true, then I must be in this case, so the output must be false. So here or true false matches the first definition, or false true matches the second definition, or false false matches the third definition. And what about or true true? Well, or true true matches both this definition and this definition, because the first argument is true and the second argument is anything. The second argument is true and first argument is anything. But remember that we will do it in order. So it will actually be using the first definition and not the second definition to compute the value. In this case, in both cases, the output is true. Okay, but something like this, which matches multiple definitions, will match the first one from the top, which succeeds. So here is a slightly more illustrative example. So supposing we want to define not or but and. Okay, so the truth table for and says that if the first input is true and the second is false, then the output is false. If it is true and true, then it is true. If it is false and true, then it is false. And if it is false and false, then it is false. Okay? So basically, this is the only case in which and will give true, which is both inputs are true. But notice that if the first input is true, then the output is exactly the second input. Right? If the second input is false, the output is false. If the second input is true, output is true. So we can now capture that in this rule, which says that if the first argument is true, then look at the second argument and return it directly as the output. If it is false, it is false. If it is true, it is true. So that's capturing these two rules. And finally, these two rules both have this common fact that the first argument is false. So it says if the first argument is false, no matter what the other argument is, the output is false. Okay? So here we are mixing, first of all, constants and variables as we did in the OR case. Okay? But we are also using the fact that the argument that we provide is reflected in the output, which we did not do in the OR case. In the OR case, we explicitly computed a constant output for each case. Here we are saying the output is a variable output depending on the input variable. So as we saw in the beginning when we are defining functions, we typically need to write functions which apply operations or compose functions an arbitrary number of times depending on the value of the input. And what we said was that inductive or recursive definitions are the way to do this. So a recursively defined function will specify a base case. So for example, if it is for the whole numbers, you would define a value for f of 0. And then inductively, for f of n, you would write an expression involving smaller values of the argument. So f of n minus 1, f of n minus 2 down to f of 0. So you can define it in terms of any smaller value, assuming that those have been inductively computed already. Right? So this is the meaning of a recursive or an inductive definition. And one of the most standard examples used to illustrate recursive and inductive definitions is the factorial function. So by definition, 0 factorial is 1, and n factorial is n times n minus 1. And of course, if you unravel this, this in turn becomes n minus 1 times n minus 2 factorial, and so on. So you get the familiar expression that n factorial is n into n minus 1 into n minus 2 down to 0. So n factorial is the product of all the numbers from 1 to n. But this is recursively captured by these two rules. 0 factorial is 1, n factorial is n into n minus 1 factorial. So now we can translate this using pattern matching very directly into Haskell. Right? So we say that factorial is a function which takes an integer and produces an integer as output. Factorial of 0 is 1, so this is the base case. If my input is already the base case, I know the answer. If it is not the base case, then I apply the rule saying I take n into factorial n minus 1. So first note this expression. So we have been careful to put n minus 1 in brackets before providing it to factorial, because the way Haskell works, if I just write factorial n minus 1 without brackets, then it will put the brackets around factorial n. So it will compute factorial n and then subtract 1, which is not what we want. In fact, that would lead us into a kind of infinite regression of computation, because factorial n is then defined again in terms of factorial n, so it will have to apply the same rule and we won't get any answer. So this is one thing to note. Another thing to note is that Haskell does not guarantee you the fact that you have written a recursive definition means that it always works correctly on all inputs. Now here, the base case 0 makes sense if n is positive, because if n is positive, then I come down to a smaller number. So say I start with 7, I'll come down to 6, 6 will come down to 5, and so on, and eventually I'll hit 0 and it will become 1. What if I start with minus 1? Okay? Factorial of minus 1 will say minus 1 is not 0, so the first rule doesn't apply, so the second rule must apply. So it will be minus 1 times factorial of minus 1 is minus 2. Then again the rule doesn't apply, so minus 2 will call minus 3, and so on. Right? So this function, as stated, works correctly for positive values of n, but because the type int, okay, so this type int includes negative values. Haskell's built-in type int includes negative values, and there is no Haskell type, built-in type, which consists of only the non-negative integers. So if I write factorial, I have to write its type as int to int, and this does not prevent me from feeding negative values to factorial, and this definition of factorial does not terminate for negative inputs. So just writing something that looks inductively correct does not guarantee that the computation will terminate for all legal inputs. So we can fix this by checking if the input is negative. So we need to now extend our syntax for defining functions to use conditional expressions to say when a definition is enabled. So for instance, we have the base case as before, the factorial of 0 is 1. Now if it is not 0, it could be positive or negative. The positive case is as before. If n is greater than 0, then I want to say that the output is n times factorial of n minus 1. But what if n is less than 0? Well, of course, factorial of a negative number is not mathematically defined, but for the sake of computation, I can always make it work by reversing the sign of the input. So if I ask you factorial of minus 6, then I will convert it to factorial of 6 and give you that answer. So at least computationally, the value will be produced in a finite amount of time instead of going into an infinite computation. So I say that if n is less than 0, then factorial of n is computed by taking factorial of minus n. So minus 6 will become minus of minus 6, which is plus 6. Okay? So what we have here is we have a conditional expression. Okay, n less than 0, and so we have this equality, remember, is the function definition. So it says that factorial of n, if n is less than 0, is factorial of n minus n, and if n is greater than 0, then it is n times factorial n minus 1. So this vertical bar, okay, signifies options. So it says evaluate this condition. If this condition is true, use this definition. Otherwise, go to the next condition. If this condition is true, go to the next condition, and so on. Right? So the second definition has two parts. Each part is guarded. So these are called guards. Okay? So it's like a watchman or a security guy saying, can you use the definition? Prove what your value is. Only then you can go forward. Okay? And we check the guards from top to bottom, and we use the first guard that works. In this case, only one of them, either n is less than 0. If n is not 0, either n must be less than 0 or n is bigger than 0. Now notice that n must be an integer, because we've already described that factorial is from int to int. So if you provide an input which is not an integer, Haskell will say this is not a legal value. So if it is an integer, then if it's not 0, it must be positive or negative, and exactly one of these things will be true. We will see later that exactly one being true is not required. But it will test them from top to bottom and pick the first guard that works. If no guard works, it will go to the next definition. The other thing to note is that we have indented this. So technically this whole thing, these three lines together, constitutes one definition. One definition with guards. Okay? So there are overall two definitions in this function, there is this line which is the base case with the pattern, and this long definition with conditional guards, which specifies what happens if the pattern is not matched. So therefore, we could have multiple definitions with different forms, right? So as we said, the first one is a pattern match, okay, and this is conditional. Now, suppose we fiddle with this definition a bit. Okay, this is not very meaningful computationally, but I can just add, I can split the second case n greater than 0 as first n greater than 1 and n greater than 0. Now notice that if n is strictly greater than 1, it is also strictly greater than 0. But because we go top down, right, if I say factorial of 2, okay, then it will say that it is not 0, then it will come here, okay, then it will say it is not less than 0, so it will come here and it will match. Okay, so though it matches the third rule, it will not reach the third rule. So the only value that will reach the third rule is what? Right? You're right. The only value that will reach the third rule is factorial of 1. Right? Because factorial of 1 will say it is not 0, so it will come here. It is not less than 0, so it will come here. It is not greater than 1, it will come here. So finally, this will only match this rule. Right? So guards may overlap. There is no requirement that the guards must be exclusive, that exactly one of them is true, so you need not worry about that. Now the other thing is, just as we saw before, that recursive definition in Haskell need not terminate. Haskell will not promise you that the value actually terminates and the function definition terminates and gives you a value. For instance, when we did not take care of negative input, factorial of -1 was giving us an unbounded computation. So here, supposing I write this definition and I have made a mistake, right? So I've got n less than 1 and greater than 1. So now if I look at the set of integers, right, then I have this for the base case. Then I have everything from -1 onwards. So this is this definition. And I have everything from 2 onwards covered by this definition. So now I have basically a problem because I have covered this, but this thing is not covered. Right? So if I say factorial of 1, it doesn't match the first case, it doesn't match either of the guards. Right? And now what will happen is that if I actually run this in Haskell, it will give me an error saying that no patterns match this input. Okay? So the function definition can miss cases, and in some situations when you miss cases, some values may give you outputs which are correct, some values. So here in this particular definition, factorial of 0 will work because it will not look at the second part. But any factorial which requires a number bigger than 0 to come down to 0, it will have to eventually compute factorial 1, right? If I say factorial of 3, it will be 3 times factorial 2, 2 times factorial 1. And when I try to evaluate factorial 1, I'll get this error message saying that program match failure. So not just if I provide factorial 1, but if I provide factorial of anything, even though the first few times it may match, eventually the recursive, this computation will come down to factorial 1, and when it comes to factorial 1, I'll get this error. Okay? So it is your responsibility to make sure that the conditional definitions cover all the cases so that no function value is undefined. So to summarize, right, a Haskell function consists of a type definition and a computational rule. Now these computational rules can be used to define, for example, recursive functions. We can have multiple rules for the same function, and the rules are matched top to bottom. And the way we define rules for different input values is to use patterns or conditional expressions to split the cases that are possible for the input values.